So let's understand what is a sampling distribution. Once we understand what is a sampling distribution, we'll understand one of the most fundamental theorems and probably one of the most beautiful theorems in whole of mathematics called the central limit theorem. Okay, we'll come to central limit theorem a little later, but first let's understand what is sampling distribution. I'll try to explain this with an example. Let's assume we have a distribution like this. Okay, so let's assume random variable x has this distribution. Note, remember, this is not Gaussian. This is not a Gaussian distribution, because if you look here, this is not symmetric, right? This tail is much longer than this tail. It could be any distribution. Okay, let's assume x follows some distribution. Okay, not necessarily Gaussian. It could be Gaussian, but it need not be. Okay, so what I'll do is from this distribution, and remember this is the population distribution. Let me make that clear. Okay, this is the population distribution. This could be distributions of incomes of people, let's say. Okay, so let's assume x is the distribution. Let me write it. X is the distribution of incomes. You'll easily notice that a lot of people, there are very small percentage of people who will make a lot of money, right? Let's assume x is the distribution of incomes, okay, of all people in the world. Okay, there will be a lot of people up. Let's just, since kids don't have an income, just let's discard them from our population. Okay, let's assume this is the population distribution. Now, what if I sample from this population? I'm picking up a sample. If you recall, when we started probability, we distinguished what is the difference between population and sample, right? Sample is a subset of population. Okay, let's assume I pick up a sample of, let's say, size small n, and n could be, let's say, just for simplicity, n is, let's say, 30. Let n could be any number, by the way. Okay, so if I take a sample of size n, okay, let me call that sample S1. Okay, so S1 is a sample, which means I'm taking, let's assume it's also a random sample. Let's assume it's also a random sample. Okay, so what I'm doing here is from all the people who have some income in the world, I'm picking up randomly 30 people, okay, where n equals to 30. Okay. I'm just picking up 30 here. We'll come to revisit why it's 30. It could be 10 or even 100 or 1,000 or a million. Okay, let it be. Okay, so I'm picking up 30 people from this distribution from x. Okay, and I'm putting them in a set S1. Okay, similarly now I'll again sample of, okay, this is my first sample, right? I'll again sample 30 individuals of size n. Okay, I'll again sample n people or 30 people in this case, and I'll put them in a set S2. And remember, these two samples were picked up independently, which means I pick up this sample and I pick up the second sample independent of my first sample. Okay, so now let's assume I keep doing this, right? Suppose let's assume I got m samples. So I did, so this is first sampling, second sampling, third sampling. Let's assume I've done m samplings. Whenever I sample from the population, I get a set S1. Let's assume that I'm computing the mean of all of these incomes. Okay, let the mean of the first sample be x1 bar. Remember, this is a sample mean. This is not a population mean. Okay, this is a sample mean. Okay, so for sets from set S2, this is set from set S2 of 30 individuals, I can compute my mean, let's call it x2 bar. So on and so forth, I can compute the mean of SM from the set or from the sample SM, I can compute the mean and I can call it xm bar. All these are sample means. Okay, so this is a sample mean, this is also a sample mean. Now comes the interesting part, right? Now I have x1 bar, x2 bar, so on and so forth, xm bar, which are m sample means sample means, right? Now, these m values also have a distribution. Given a bunch of numbers, I can compute its distribution, right? Because I can compute, or PDF for that matter. That's what I mean when I mean a distribution, right? So the distribution, so these xi bars will have a distribution. These xi bars will have a distribution. The distribution of xi bars, the distribution, I'm a little lazy to write the whole word distribution, so I'll just write this, okay? The distribution of sample means, okay? But what are these samples? That's important to remember, okay? So this is a, so I can write xi bars as, okay, the distribution of xi bar. I can write the distribution of xi bar. Distribution of xi bar is called the sampling distribution of sample means. Okay, remember this is a big tongue twister and also a brain twister. Okay, I don't know if that word is familiar to you, or I don't know if I just made it up. It basically is very confusing. Remember the parts of it. That's important. So what is a distribution of? It's a distribution of sample mean. Okay, that's important. And how did we get the sample means? From a sampling distribution, through sampling, right? From the population distribution we sampled and we computed the means of it. So the distribution of xi bar is called the sampling distribution of sample mean. This is a twister here. Okay, so it's a distribution of sample means. And how did we get the sample means? Through a sampling process. So it's called the sampling distribution of sample means. Now you might understand why are we introduced to this topic, so as to set the stage for central limit theorem. Let me explain you the central limit theorem, which is very fundamental and probably one of the most beautiful ideas in whole of statistics and probability, and probably in the whole of mathematics, if I may say so. So what central limit theorem says is, if our original distribution x, if our original population distribution x, right, this distribution here, okay, if my original population distribution, if x has finite mean and variance. Now you might ask, when do we have infinite means? Okay, is it possible for us to have infinite mean and variance? Yes, there are some distributions out there which have infinite means and variances, like Pareto distributions. Okay, I'll not go into the details of it. Those of you who are interested, you can just Google it up. You can Google up the mean and variance of Pareto distributions. You'll find that it's infinity. It's actually not defined in some cases. It's not defined in some cases, sorry. So there will be distributions which have infinite mean and variance. For those distributions, central limit theorem will not work. The one that I'm defining here. There are extensions to central limit theorem that work, and there are many forms of central limit theorem, because it's such a fundamental theorem. There are many ways of writing central limit theorem, and there are lots of extensions even to distributions which have their extension. It's a very fundamental area of research even today. What happens to central limit theorem when you have a random variable x which has undefined or infinite mean and variance? But for now, let's stick to our world, the simple part. Let's assume x is a random variable with finite mean and variance. And let's assume I start sampling from x. Okay, let's assume I've created samples S1, S2, so on and so forth, Sm. And let's assume each of them are samples of size n. This is important here. Okay. Now for each of these samples, I can compute the sample average or the sample mean. Let's say x1 bar is the sample mean. Okay, these are sample means. Similarly, for set S2 or samples S2, I can also compute the sample mean, which is x2 bar. So on and so forth, I can compute xm bar. Now comes the best part. What central limit theorem says is, right, what is this? This is, so I can say that these things have a distribution, which is xi bar. And what is it? What is the distribution of xi bar? The distribution of xi bar is called the sampling distribution, of sample mean. We just learned that, right? I just defined what is a sampling distribution of sampling mean just a while ago in the previous discussion. Just right here. Now the distribution of xi bar is called the sampling distribution of the sample mean. What central limit theorem says is that xi bar is distributed, sorry, not tilde, bar, sorry, my bad. So xi bar is distributed with a Gaussian distribution. Okay, this is a normal or a Gaussian distribution, with a Gaussian distribution of mean mu and a variance sigma square by n as n tends to infinity. Now let me break it up for you. This is very, very important. And this is super beautiful. I'll explain you why. Just bear with me. I've just written the equation here. I've just written the theorem here. Okay. Let me repeat it for you. If x is a random variable with finite mean, population mean, this is population mean of mu and variance of sigma square. And if I take samples of size n, here is my n. Okay. If each of my samples is S1, S2, S3, if I've taken m such samples, and if I compute sample means as x1 bar, x2 bar, xm bar, there is a distribution for xi bars, which is nothing but the sampling distribution of sampling means. What central limit theorem says is that xi bar will have a Gaussian distribution with the mean mu. This mean is same as this mean. Okay, so xi bar, the mean of xi bar, this is important, which means it will have a Gaussian distribution with the same mean as the population mean. And the variance of your xi bar will be sigma square by n. Here is your n. So this n comes here. This sigma square comes here as n tends to infinity. Okay, so let's understand what it means. I mean, the theorem part is clear, right? So what it literally means is, if I have any distribution x, if I take samples, okay, and if I take, let's assume these are incomes. That's a better way to understand. Let's assume these are incomes with a mean of mu and a variance of sigma square. Okay, this could be any distribution. It need not be Gaussian. That's very, very important. Let me write it very clearly. Need not be Gaussian. Every distribution has a mean and variance. Okay, sometimes not defined, sometimes infinite. Okay, but x need not be Gaussian. That's very, very important and critical. Suppose if I've sampled S1, S2 of sample size n. Okay, so let's assume let n be equals to 30. Okay, so I've taken, so these are my incomes, right? I said these are my incomes of all income earning people in the world. Okay, so this is the sample of 30 people and their incomes. This is a sample of 30 people and their income, so on and so forth. And now this is easy, right? So let's assume m equals to 1000. Let, which means I just needed to compute 1000 into 30, which is 30k people's incomes I just needed to take. Okay, this is your m and this is your n, right? So I just collected 30k samples, 30k observations, not samples, sorry. I computed 1000 samples of sample size 30, which means I've literally taken data of only 30,000 people. Now, if I compute the mean of each of them, I'll get x1 bar, x2 bar, so on, so forth, xm bar. Again, these are the mean incomes in each sample. These are the mean incomes in each sample. And I have 1,000 of them because m equals to 1,000. If I plot the distribution of this, okay, if I plot the distribution of this, I get a Gaussian distribution. I get a Gaussian distribution with a mean. So if I take the mean of xi bars, okay, this mean is roughly equal to the population mean. It's roughly equal to population mean. So I can compute, I can estimate my population mean here. I can estimate my population mean by taking the mean of xi's. So this will be mu, and the variance and the variance and the variance of xi bars, which I can compute from data, right, will be equal to sigma square by n. Typically, again, the theoretical part, if you recall, the theoretical part says this is true as n tends to infinity. But in the real world, if your n is greater than equal to 30, again, this is a rule of thumb. This is a rule of thumb that statisticians have come up with. If n is greater than equal to 30, okay, if n is greater than equal to 30, this distribution becomes Gaussian. Which means by just looking at 30,000 data points, I'm able to estimate the whole population mean and population variance. Which means to understand population mean and population variance, which are my mu and sigma square, of any distribution, to understand what is a population mean and variance, I just need to know that they're finite and they're well defined. That's the only thing I need to know. For any distribution, I can estimate it by doing this simple sampling exercise and computing the and getting the sampling distribution of sampling means. Okay, this is nothing but the sampling distribution of sample means, right? So CLT says that the sampling distribution of sampling means for any population with a finite variance and a finite mean is a Gaussian distribution with a mean tending towards the population mean and the variance equal to sigma square by n as n tends to infinity. But as soon as you have n greater than equal to 30, these things will start falling in place. So for any given random variable, you can estimate its mean and variance by using the sampling distribution of sampling means very, very easily. This is why it is so powerful. This distribution could come from anything in the universe. Any distribution, it will take care of it. That's why central limit theorem is such a fundamental idea in probability and statistics.